Every day, the future's getting closer.
Welcome to Master the NEC, where we talk about the National Electrical Code and all things electrically related. My name is Paul Abernathy, your host, and welcome to today's podcast. Well, hello everybody. Welcome to another episode of Master the NEC, where we talk about the National Electrical Code and all things electrically related. My name is Paul Abernathy, your host, and I want to welcome you to today's podcast. So today's podcast, we're going to talk about non-dwelling load calculations. So we spent a lot of time doing residentials, a lot of time doing the standard optional methods and all that. But I've had a large request for people to say, Paul, can you kind of walk us through the steps for an application in a commercial building where you got a non-dwelling load calculation? So there's a bunch of different steps that you go through, and so we're going to talk you through all that. Now, what we're going to talk about today is basically following or mirroring our lesson plan in our Fast Tracks program that we offer on our website. So we're going to kind of use those same values because the students that will be using that will also be listening to this podcast, and so they can kind of relate to the topic at hand. If you're not in the Fast Tracks program and you're just following along, then I'm just going to give you values to consider. There's also going to be portions of this that I'm actually going to reference you back to another podcast or another video because it would just simply take too long to go into some of the details of one of the steps other than to simply tell you about the step itself. And you'll know that when you get there. I'll make reference to that and probably give you some overlining guidance first before I reference some other document. But we're going to try to cover each of the steps. So we're going to talk about non-dwelling load calculations. We're going to deal with the lighting, the general lighting, specialty lighting, receptacles, whether we're dealing with them as a non-continuous, in some cases later as a continuous load to maybe some piece of equipment that's cord and plug into a receptacle or something. We're going to take all those things into consideration, even fixed multi-outlet assemblies if you happen to run into those. We're going to talk about applying demand factors to the receptacle loads as well as demand factors to the lighting loads, if it's applicable or not. We'll discuss that. And we'll move through the kitchen equipment when you have to be able to apply demand factor for the 3 or more pieces of kitchen equipment. We'll talk about all that, and of course we'll round all this out with non-coincidental loads as well as all the other loads that we might miss in these steps to treat whether they're continuous and non-continuous, and we'll kind of work from there. So as you can guess, we're doing a non-dwelling calculation, feeder or service, doesn't really matter. We're trying to determine a total VA for this demand load for this non-dwelling building, store, bank, or whatever it might be. And that's what we're going to work it through. Now, as we go through, I'm going to give you different scenarios that kind of call out each specific part that might be give more clarity to it. So just kind of follow me along here. This is going to be quite an extensive video. I'm 3 minutes in, and I'm going to tell you this is probably going to be over an hour. I don't know when, but this is extensive, and I want to make sure I cover every step the best I can. All right, number one, the first thing that I do when I think about a non-dwelling or commercial building is I'm thinking about, did the engineer specify certain receptacles and the number of them and where they're to be? Because again, it's not like residential where I place them every 6 and 12 feet, depending on if I have a doorway and all this kind. I don't have that here in a commercial application. All right, and from here on out, let's kind of make it simple. Either you're dealing in a dwelling application, which we'll say is residential, or we'll say the non-dwelling is commercial, and we'll leave it simple. Okay, commercial could also apply to things like industrial, but again, I want to keep it simple here, either residential or commercial. And so what we're talking about today is commercial. Okay, the difference between a dwelling application and a non-dwelling. That's what we're talking about. We're talking about the non-dwelling component. All right, the first thing I like to do is when I get a plan or whether I'm calculating something out or trying to determine is, does it tell me how many receptacles that I've got? And that's important for me because in a commercial application, we need to take a value of each strap or yoke of a receptacle. Now, let me explain that. 220.14i, it tells you that you take each strap or yoke of a receptacle at 180 VA. Now, it would not matter if on that strap or yoke, that's the metal piece that actually holds the plastic portion that you plug an attachment plug into from an appliance, okay? That's the part you plug into. That device could have one receptacle, two receptacles we refer to as a duplex, a single one we refer to as a simplex, or even a three would be a triplex receptacle. Either way, if it's on one yoke or strap, it equates to 180 VA. Okay, and that's the volt amperes that we're going to use in our calculations, okay, for these receptacles. Whereas in residential, we don't use 180 VA. There isn't really a limit to the number of receptacles we can have on a circuit, except for obviously the load itself. But receptacles aren't considered a continuous load, so there is no rules in dwelling applications or residential. Whereas in commercial, we are limited to 180 VA per strap or yoke. Okay, now again, it doesn't matter whether it's a single receptacle, duplex receptacle, or triplex receptacle, it's still 180 VA per yoke or strap. And that gives us that in 220.14i. Now, one thing to remember is sometimes we have these pieces of equipment that consist of 4 or more receptacles on the piece of equipment. Okay, and it's usually flat. It's usually the size of a 4x4 square box or 4x4 and 11/16 box. And it mounts on front of it or mounts in it, and it's got 4 receptacles or more on the surface. If that's the case, then we calculate each individual receptacle at 90 VA. Okay, so if it's a 4 or more on this piece of equipment, this kind of a real big receptacle, if you will, with 4 different openings on it for attachment plugs, then it would be 90 VA each. Okay, so if there's 4 of them, it'd be 90, 90, 90, 90, 360. One thing to remember, if it's a 4-inch square box and I've got 2 duplex receptacles in it, then it is going to be based on each strap. So it's 180 per the one strap and 180 per the other strap. That's a total of 360 as well. You see what I'm saying? So just remember, when it's a piece of equipment that consists of 4 or more receptacles, then it's actually calculated at 90 VA per receptacle. Okay, again, all that's expressed in 220.14i if you want to go check that out. All right, so the first thing I do is in a building is I look and see how many receptacles we have, and I'm going to add them up. So in our example, let's say that I have a total of 75 duplex receptacles, and I have 10 single receptacles, which I refer to as simplex. Okay, duplex, simplex, triplex, you get my point. All right, so it has a total of 85 receptacles. There's 85 straps or yokes. It just happens that one strap might have the duplex, and the other one has the single receptacle, which is a simplex. Either way, each one of those straps or yokes counts as 180 VA. So my first step that I want to do is I'm going to take the 85 times 180 VA, because that's what 220.14i tells me to represent each strap or yoke of a receptacle. Again, we're talking about commercial application, not residential. Commercial. So that equals 15,300, which is 85 times 180 equals 15,300. So that's my VA, the first one that I write down. So that's kind of my step 1 scenario. All right, so the next thing that I'm going to do is I'm going to go through my list and say, well, and again, remember, general use receptacles are not considered continuous load, okay? They are not. They are just a receptacle for general use purposes. So the next thing I look at it and say, well, do I have any fixed multi-outlet assemblies? Now, this is a track where you generally have a track, it's kind of like a plug mold, but it's a track with individual receptacles inserted into the track, and that's called a fixed multi-outlet assembly. And so the code tells me that when I'm dealing with 220.14h, that I've got 2 things to consider for a fixed multi-outlet assembly. Now, if these receptacle track is 75 feet long, okay, let's say linear feet, a total amount of this fixed multi-outlet assembly is 75 feet. And let's say that I have 15 feet of that 75 is considered simultaneous use. That means that I can use any of those receptacles that are in that 10-foot section. I am likely to utilize multiple loads at the same time simultaneously in there. Okay? It is known to happen. It's going to happen. Or the engineer either specifies it or you know it's going to happen. If that's the case, then 15 feet of that is considered simultaneous use, But then the remaining part of that 75 feet minus that 15 is 60 feet. And that would be non-simultaneous use. It means it's just being used at random. Okay, it's not likely that that's going to be used simultaneously with multiple loads on it. Okay, now if that's the case and the engineer designs this and specifies this, we're going to assume in our example it's 75 feet, 15 feet is considered simultaneous, and 60 feet is non-simultaneous. So here's what the code says. H1 says that we're not likely to use any of this fixed multi-idle assembly for simultaneous use. You're going to multiply each 5-foot section or fraction thereof by 180 VA. Now, when I say fraction thereof, maybe I have a piece that's not 5 feet long. Maybe I have a piece that's 4.5 feet. It doesn't matter. You're still going to take that because that's a fraction of. You're still going to take that as 180 VA. Okay, and that's what you're going to equate with that. Now it says, what about the portion that is likely to be used simultaneously? Well, if that's the case, then the code says that I'm going to take each foot as 180 VA. In our case, we had 15 feet that was simultaneous, so I'm going to have 15 feet that I'm going to do at 180. So how do I do the math? So let's deal with the non-simultaneous use first. So there was 60 feet of it, and the code says that every 5 feet we take it 180. So I want to find out how many 5-foot sections I have. So I take the 60, I divide it by 5, and that tells me I got 12 5-foot sections. Okay, so now I'm going to take that 12 times 180 VA, and that's going to be 2,160 VA. Okay, now that's my non-simultaneous use portion of that fixed multi-idle assembly. Now I got to deal with this 15 feet. Now, if you remember, the code says that I take it each foot at 180 VA. So I got 15 feet. So the math is pretty simple. 15 times 180 VA is 2,700 VA. Okay, so I'm going to add those two together because that's my total values, both the simultaneous and non-simultaneous, for that fixed multi-idle assembly. So that add them together, and that's going to be 4,860 VA. So I'm going to write that down. So that's my second receptacle value. So I've already done the general use, I've done the fixed multi-idle assemblies, and now I got these two receptacle values. Remembering, they're not considered continuous load at this point. They're just general use receptacles. Okay? All right. So the next thing I know that the code tells me, it says, you know what? In a normal commercial application, I've got receptacles, and I get to apply a demand factor to this. So next thing you look at is 220.44. Now 220.44 tells me that I can take the first 10,000 VA for this receptacle loads and take that at 100%. Okay, in other words, the first 10,000, I can take the first 10,000 kVA at 100%, and then the remaining portion over that at 50%. And it doesn't give a plateau on this. It just tells you flat out that I can take the first 10,000 at 100 and everything after that at 50%. So in our case, we took our values. So how are we going to apply what we just did? Well, we added the two together. That's 15,300. Okay, and then we added the other, which was 4,860. Right? That gave us total. We added the two together, 20,160. Now, the first 10,000 is 100, so I'm going to take 10,000 away from 20,160. That leaves me 10,160 left over. That's the amount that I multiply by 50%, which is 5,080 VA. Now, I add back the 10,000 because remember I said take the first 10,000 at 100. So that's 10,000 plus the 50%, which was 5,080. That gives me a total of 15,080 VA. So I'm going to write that down as step 3. Now, step 3 is the culmination of step 1 and step 2 brought together and now applying a demand factor. You get me? So that's why we're going to jump now to step 3, and that's our demand for these receptacle loads, and that's what we're going to use in our calculation. All right. Now, in any other aspect of a commercial application, that would be where we would stop with that general use type receptacles and the fixed multi-outlet assembly. However, if our application in our building happens to be a bank or an office building, I got to do one more step. Yes, I take the values that I just did. Let's say this building we just did is a bank, and we already did our load calculation because of the receptacles that were designated on the drawing and the fixed assemblies that were dedicated on the drawing. And we came up with 15,080 VA is what ended up being our demand load. We wrote that down. When you're looking at the code, now that we're dealing with banks and office building application, we also have to look at 220.14K. Now, 220.14K is basically saying, I need to look at what you just did in 220.14I. I need to look at what you just did, and I need to say, you know what? Take that value in what you did and demands that you applied to that, and now I need to compare it with the total square footage of this building, this bank, at 1 VA per square foot. And whichever is larger, that's the one I'm going to take. Okay? So in our case, if it was an 8,500 square foot bank, and we're trying to compare what we just did in step 3 to what we get here in what I call step 4, if it's a bank, and you might not have a step 4 if it's not a bank or an office building, but let's say ours was. Now I have to compare the options of 210.14 K1 versus K2, and I got to take whichever resulted in the larger. Well, we already did the calculation for K1, which is what we just did, coming up with our values in step 3. Well, step 4 says, well, you got to take the square footage outside dimension of this bank times 1 VA, and that is a clear, easy calculation. 8,500 times 1 is 8,500. Is 8,500 greater than the 15,080 we just did in step 3? Absolutely not. So I get to discount the 8,500 and I don't even have to use it. I got to use the 15,080 VA that we just did earlier. Now, with that said, what if you get an application where you didn't have a step 1 and step 2 for the general use? You didn't know anything about the receptacles. They didn't tell you how many numbers you had. And you're simply given a bank and an office building or something, and you don't know these values, right? Then if that's the case, if you're dealing with a bank or office building and they don't give you those values, then here you're going to use the K2 option, and that's simply going to be the square footage times 1 VA, and that's going to give you, in this case, was 8,500, and that's the value you're going to use, okay? So if you know the actual number of general purpose receptacles and outlet, then you're going to obviously compare the two. If you don't know or it's not provided, then you're going to have to go with the square footage at 1 VA per square foot. And again, that applies to only banks and office building applications. Which brings us to the point, any other building other than that, the engineers are going to have to specify out the receptacles and where they're at so that you can come up with a general receptacle load calculation, okay? This step right here, step 4, only applies if it's a bank or an office building, okay? Just to make that clear, okay? And that's only applies to that. All right, so now at that point, we have done our receptacle calculations, all right? And now we're moving into the general lighting loads. Now, general lighting differs from what we did in a residential because the general use receptacles were wrapped up inside of the general lighting by 220.14J when we're doing a dwelling unit. Not the case here. We had to do a separate receptacle calculation. Now we're moving into general lighting. Now, the general lighting is the general lighting. That's the lighting we need to create the daily function and move through the store or the building or the bank or whatever. That's our general lighting. Later on, we'll have some specific lighting, like track lighting, show window lighting, and things like that. That's different. That's additional loads that we have to take into consideration. Right now, we're just talking general lighting. So let's use our bank to kind of wrap onto this. So remember that bank that was 8,500 square feet? So under the general lighting, you're going to go back to what you're all probably familiar with, 220.12, which talks about general lighting loads, and it's going to reference table 220.12. And 220.12, you're going to notice that there's a long list of VAs there per square foot. And these are values that are going to be given you, and as you look through them, you're going to notice that this is your general lighting by occupancy type. So in our case, if we said it was a bank, you would go down this list and you see that a bank, second one on the list, is 3.5 VA per square foot. Now you notice that little B? That B is just reminding you of what we just did a minute ago. If it's a bank, then the receptacle calculations have to be done in accordance to 220.14K, and you have to compare the difference between or K1 or K2 and do that math. And we just did that. So that's just a reminder. All right, but you see here it says 3.5. So you need to convert this to a decimal, so that's 3.5. So we take, and remember before how we've done in our dwelling calculations, we're going to take the square footage area times the VA per square foot unit load. In our case, 8,500 times 3.5 is 29,750. So that's our general lighting load. Okay, now let's just say it was a convenience store. Okay, if it's a convenience store, then we could go on, and let's say the convenience store is 30,000 square feet. So we could go 30,000. The general lighting would be, and we come over here to this unit load here on table 220.12. We're coming down to store, and we see that stores is 3 VA per square foot. Okay, so that would be 30,000 times 3 VA equals 90,000 VA. That would be your general lighting load. Okay, all right. So that's how you calculate your general lighting load. Now, that is step 5. Now, step 6, and you write that down, by the way. That's your load. You write that down, and that is your load for that application. Now, step 6 is when we want to say, well, when can we apply a demand factor to our lighting load, our general lighting load? Can we apply demand factor? Can we get a little bit more of a break? Well, that kicks us into table 220.42. Now, if you look at 220.42, you'll notice the type of occupancies on this is very limited. Okay, hospitals, I can get a break, and I can't get a break in hospitals in those areas that are going to be where I'd have continuous loads, or the lighting would be on at all time, or other simultaneous lighting like ballrooms, dining rooms, operating rooms. Then we know the loads are going to be on continuously 3 hours or more. I mean, those aren't really what you're using this table for. And in fact, you can't apply the demand factors of 220.42 to continuous load applications, okay? So you need to define out in a building whether or not, if these demands applied, are the loads that we're talking about continuous or non-continuous, okay? Any lighting that's going to be on for 3 hours or more is going to be a continuous load. Okay, so just things to consider as we're moving through this. And you see that the list is very limited. Now, obviously, we're not going to talk dwelling units because we've already done that at nausea in other podcasts and videos. So we're going to go down the list. Now, we did a bank and a store. They're not listed here. So they would fall down under the list here where it says other, all others. And you see it's 100%. So we got to take the values at 100%. And so that 90,000 for the store or that 29,750 for the bank, that's the value that we're going to use. Okay. Now, before I jump into an example of when we can use a demand factor, I want to remind you of something. When you're doing the general lighting load, if I have different types of occupancies involved, then I can use the different classifications here, or types of occupancies, in order to do my calculation. Let me give you an example. So maybe I have a situation where I have an assembly hall and an auditorium. Each have a load value of 1, but then I have hallways, corridors, and stairways that are incorporated in this occupancy, and those are separate areas, and they have their own value here. So I might have a unit 1 load for the assembly hall and auditorium, but when it comes to the hallways, the corridors, and various closets, and even the stairway, that's different. That is a half of a VA, volt ampere per square foot. So in this case, it would be a 0.5 per square foot, all right? A 0.5 VA. So you see that I can pick and choose and dissect different portions. And so let's say I had a hospital. I could do the exact same thing for the corridors, the hallways, and anything that would fall into this occupancy class, okay? I can piecemeal it. Now, that brings me to the use of, when we get to step 6, if it's applicable, is let's talk about a hospital. Now, in a hospital, and again, I'm doing everything the same up to this point, but now I'm determining whether, and because hospitals do have a VA as well. You see here, it's 2 VA per square foot. But maybe a hospital, since it's listed under 220.42, I get to apply some demand factors to this load, this general lighting load. Okay. Well, in my case, I know that I have what's called patient rooms. And those patient rooms fluctuate a lot. They're usually, the lighting is not on 100%. It's not on for 3 hours or more. The patients control that. It's not a location that has to be lit at all times, like the corridors and the dining facilities and all of those locations where the lighting is going to be on for 3 hours or more. The same as in a dwelling unit, we don't take the lighting loads as a continuous load, even though we know that somebody can leave that light on for 3 hours or more. There's diversity involved. So here I take the liberty of saying, you know what? Those patient rooms are not going to be treated, and they're not all going to be on simultaneously. And so I can take those and I can apply demand factor to those. Okay, so I'm taking the liberty of doing that. So again, I might have corridors. I have to take that into consideration as general lighting loads, and that might be also continuous loads. And I have to denote that as a continuous load. And I'm going to explain that here in a second, how to do that, because you see up to this point, I didn't say anything about continuous load for lighting yet. I'm doing that purposely. Just listen to me. All I've done at this point is simply try to calculate loads. All right, now, so take a hospital. So the hospital, it does allow me to apply demand factor, and I'm going to say that I can only apply it to the patient rooms. There is diversity there. And so let's say I have 100 square feet of room dimensions, the outside dimensions of the rooms for the patient's rooms in this hospital, and it totals 100,000 square feet. Okay. Well, if I go and look at table 220.12, and you scroll down and you can see hospitals that has a 2 VA per square foot, and I had 100,000 square feet. Okay, so I'm going to take 100,000 and I'm going to multiply that by 2, and that is 200,000 VA, right? Okay, now this is when I get to apply demand factors for that specific portion of this hospital that I've determined is applicable to 220.42. All right. And in this case, I'm going to look at the demands, and it says, okay, for a hospital, the first 50,000 or less at 40,000. Well, we know we're going to use that because we have 200,000 here. The next, it says the remaining that is over 50,000 is just at 20%. Wow, I get a large diversity here. Okay, so how do we do this? So the first 50,000 I'm going to take and I'm going to set aside, and I'm going to take that 50,000 and now I'm going to multiply that by 40%. So that's 50,000 times 40%, which results in 20,000 VA. I write that down. That's my first step. Now, what about the portion that's over 50? Well, the portion that's over 50 is 150,000. Remember, because our total was 200,000. You take 50 away from that, that's 150. So that portion that's over 50,000, I get to apply 20% demand factor to it. So it's 150,000 times 20%, and that equals 30,000. So now I add the two figures together. The first one was 20, and the second one was 30. So my total VA for these patient rooms applying this demand factor is 50,000 VA. And I can plug that in as my general lighting demand factor. Okay. Now remember, in a hospital, I have other areas to take into consideration. And so I might also still have step 5. I might have other general lighting loads that were not subject to this demand, that I have to take them as what they are. Okay. So keep that in mind. All right. Now, before I even move on to the track lighting and sign lighting and showroom lighting, this is the point where I start talking a little bit about continuous loads. The general lighting loads that are going to be on for 3 hours or more are going to be taken at 100%. Now, the calculations that we just did, we took straight VA. Okay, based on whatever was in table 220.12, we did our calculation. That is straight VA. You're not going to add the 125% or the additional 25% at this stage for anything. Not our track lighting, not our sign lighting. Even though they will be continuous loads, we're going to wait and add that later in another step so that we can add these all up. So when you're doing this is where I start telling you to take your pen and put a little asterisk right next to your calculation that you're doing per step if those loads are considered continuous loads, so that later you can go add all of those with the little star beside it and then apply it times 25% in order to find that additional little bit that you get to add in there for the continuous load. Okay, that's just how I explain it. It makes it easy to understand it. All right, and the reason it makes it important is because I just had a load that was a demand factor that I didn't consider continuous, so I wouldn't put an asterisk there. but I might have other portions that are part of the general lighting in that building that are considered continuous, and I want to make sure that I put a little asterisk beside that because I'm going to need to add the additional 25% to that value later on in my process. You follow me? All right, so it just makes it easier to follow along. Okay, so if I was dealing with a hospital, that's what I would do. The demand factors applies to that specific portion, but I still have other general lighting in that building that I might have to deal with, and I take those as what they are. Okay, now what about that bank and that store we just did? Those values that we did, $29,750 for the bank or $90,000 for the store, yes, that would be a continuous load. So I want to make sure I put a little asterisk beside that because we're going to take that value in step 5 and add it to our step when we get to the continuous load. You get me? Just put a little mark there. Okay? Don't change the VA values yet. Just put that mark. That's all we want. Okay. Move on to the next stage. Now in lighting, we're moving on to lighting that's not part of the general lighting. This is additional. Okay, this is additional lighting loads that might be there because of the design or somebody's designing it. And track lighting tends to be if we're doing it to highlight a specific widget that might be there on the wall or something like that in a store or something. Okay, so what does the code say? Well, we're going to talk about a store. We're going to keep it as a store. If you look at 220.43b, it says, is this track lighting now? And let's say we have 80 feet. We have 80 feet of track lighting. So when you look at the code and we look at 220.43b, I'm going to do it with you. If you're following along in your car, don't worry, I'll do it for you. It says track lighting in other than dwellings. So the dwelling unit track lighting is all associated with the general lighting anyway, so you don't have to do anything extra. As well as for guest rooms and guest suites or hotels and motels. And that's what we're talking about. It says an additional load of 150 VA or volt amperes shall be included for every 2 feet of track lighting or fraction thereof. Okay, so if it doesn't become exactly whole rounded to every 2 feet, it might be 4.5 feet. Okay, well, it's 4.5 foot of track. You have 2 foot, and you have a half of a foot. That's a fraction thereof. So we would have a 2 foot, and then a 2 foot, and then that fraction would also count as an additional, that would count as 150 VA for the first 2 foot, second 2 foot, and even that fraction would be another 150 VA. You get what I'm saying? That fraction, any part of it counts. All right, now, so what we got to do is, we knew we had 80 feet. That's just give you that example. We have 80 feet. Now, the first thing I'm going to do is divide that 80 by 2 because it is every 2 feet. So I need to break it down into a number of 2 foot sections. It makes it easier to do the math, right? So 80 divided by 2 is 40. I have 42 foot sections. It was 150 VA per 2 feet. So I'm going to do 40 times 150 VA. That results in 6,000 VA. So that's my next step. That's step 7. And I'm going to write that down. And that is going to be 6,000 VA. And I'm going to put a little asterisk beside that because if it's a store, then that is going to be on for 3 hours or more. It's a continuous load. I need to take that into consideration. Okay, so I write that down. And that's where I put that little asterisk there. Okay, now moving on. The next thing that we'll look at, and we'll kind of jump out of sequence, but I'm going to move on so we don't lose track of the requirements in 220.14 systematically through A, B, C, D, E, and everything we do. We need to look at the signs and outline lighting. So we are dealing with the commercial, and every commercial building or occupancy within a commercial building that is actually open to a pedestrian has to be provided with at least one outlet location accessible to each tenant space entrance for a sign or an outline lighting system. Now, this is all covered in 600.5a, and it's a minimum of at least 120 amp that's got to be devoted just to this with a dedicated circuit. Okay. Now, here in our calculations under 220.14f, we're doing a calc. So we need to know what the minimum VA to use is in our calculation for each one of these required sign or outlining circuits when we're doing our load calculation for feeder or service. So in our case, it's a minimum of 1200 VA. Now, I'm going to remind you of something. If we have a sign or we have an outline system that has a nameplate with a VA value that is greater than 1200, then we have to use the greater value. This 1200 is just the minimum. This is the minimum if we didn't know any better. So we have to have at least 1200. But in reality, when we're designing this, usually they know what sign's going and it's going to be on the plans, and the engineer knows this VA value. And let's say the value was 1800 VA, and you know the minimum is 12, but it specifies out 1800. Yes, you have to use the 1800. You don't use the 1200. You got to use whatever is specified out, but the minimum is 1200 in our calculation. Okay? All right. So that's step 8 if it's there. Okay. Now, another reminder is you might sometimes have corridors or service halls that are not for the general public. Like in malls, sometimes you have those corridors that are behind or that are kind of locked behind. It actually is service to bring in goods and stuff. Those don't require sign or outline lighting at those. Okay, so that's not figured in. It's only the ones that are accessible for the pedestrians, okay, out for general use. They're the ones that require to have that sign or outline lighting at each occupancy, okay, that's accessible to the general public, okay, at each tenant space. All right, so assuming we've done that, we would add that value here. Now, if I've got a space that's got 2 entrances, then I'm going to have 1 for each entrance. So a minimum of 1200 each, okay? That's how we would do it. So the next thing we're looking at is let's talk about show window lighting, if that happens to be something that's in our situation or in our equation in this design. All right, so let's say we're still dealing, let's stay with the store. So I have the store and I have show window lighting. This store is in a mall, and I have this show window lighting, and let's say I have 75 linear feet. And how do you measure that? You measure it horizontally along the show window's base, okay? So that's how we measure it. And let's say I have 75 feet of show window space. Now, what does the code tell me that I have to do? All right, so for show window space, we're going to look at 220.43a, and we have to understand that it also gives us direction in 220.14g when we're dealing with the branch circuits that are feeding these show window lighting. Again, it's still going to be 200 VA per linear foot. But here we're trying to do a calculation for the feeder or service. So in here, if the occupancy has 75 feet of linear show window, and we're dealing with a feeder or service load, then it would be 75 times 200 VA. Now, where do we get the 200 VA? So you want to look at 220.43a, and I'm going to do that with you. And as I look back at it, you'll see show window. And it says for show windows lighting, the load of not less than 660 VA for linear meter, which we don't use. Typically, I would not use. It would be 200 VA per linear foot shall be included for the show window measured horizontally along its base. Okay, so we had 75 feet, 200 VA per foot, 75 times 200, 15,000 VA. So that's what my show window lighting VA is going to be. And that's just step number 9. You're just following down the list. Boom, 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 boom. And I would write that down. Again, if you have no show window lighting, you're not going to add it. Okay? If you had you're going to have sign and outline lighting on a commercial space because there is going to be an entrance to the public. Okay? But you might not have track lighting. You might not have show window lighting. So, again, you're only going to apply these steps if they're applicable to whatever your calculation is. Okay? Another thing to remember, the show window lighting, the sign and outline lighting, the track lighting, and in most cases, the general use lighting in areas are going to generally in commercial applications be considered continuous loads. So you remember, I'm going to have this little asterisk all along the side. Okay? If it is going to be used as a continuous load, okay, and that's 3 hours or more continuously, maximum output. And again, lighting generally is at its maximum output. Whatever the lamp rating is, it's generally burning on, it's gone. All right? So that's our steps. Now, what we've done is we did step 1, step 2, step 3, all the way up to 9. Step 1 and 2 were a culmination that resulted in the values that are in step 3. So from here on out, we're pretty much talking about the steps that we moved from step 3 on. Okay? And so now we've moved from all of the lighting aspects. Now we're looking at how do we address those continuous loads that we just talked about all the way up to this point. So now I'm going to take care of that continuous load. Now here's why I do it this way. Because if you do each step and you mark to the side which one is to be considered a continuous load, you're a lot more accurate than simply taking the load at the time you calculate it and do it at 125% and write that down. It just is more accurate to wait and do all of your continuous loads together as one lump sum. Okay? Now, that's what's going to be step 10 for us. And now in step 10, we're looking at all those continuous loads that we covered. Now, obviously, the general use receptacles that we covered in step 1 and 2 and culminated in the total general receptacle application in demand factors in step 3, that is not a continuous load. So we're ignoring those applications. In our case, when we did an example of applying the demand factors in 220.42, the patient rooms we did not consider a continuous load. So that was discounted. But we might have other general lighting loads in that hospital that would be considered continuous loads. Also, we had that store. That's a continuous load for the general lighting. The bank, that was a continuous load for the general lighting. So I'm going to take all of those values that I put the little asterisk beside. I'm going to add them all together, and that's going to be in step 10. I'm going to take all of those, add them up, write them down, and I'm going to multiply that by 25% because I've already got the 100% value for all of these loads. I just need to take their value at 25%. And it would be no different if I took each one of them by 125%. I just like to do it as a group. It just makes it much easier to do that. Okay? So, put down your total loads there that you calculated in all of your steps coming up to this point. And do it times 25%, and that value goes right there. Okay? That's what that value would be. All right, so we've done 10 steps. Now we're done with our receptacles and our general lighting. Now we're going to move on to kitchen equipment. Now, when we talk kitchen equipment, we are not going to use 220.55 for household cooking. We're going to leave that to the dwellings. We're going to leave that for instructional programs like home ec in a school. We're going to leave that at 220.55. We're not going to deal with that. We're going to be aware of the Notes 5 and all these other things. We're not going to worry about that. We're talking about all other electric cooking equipment, dishwasher, booster heaters, water heaters, all of these appliances that are, one, thermostatically controlled, or that is intermittently used as kitchen equipment. Okay, they're intermittently, it goes on and off. It doesn't, so it's either thermostat controls it, clicks on and off, or they're designed to have intermittent use inside the kitchen area. Okay, so if we meet all of those things, and that's generally going to be most of the appliances that we're dealing with in kitchen equipment. Okay, so let's kind of look at it. So let's say we had a commercial electric cooking equipment. It'll have a nameplate value. We have the dishwasher booster heater. We have a water heater. And we have other kitchen equipment. And we're going to use table 220.56. Now, 220.56 is a way for us to apply demand factors to the actual nameplates that are on these kitchen appliances. Okay? So, if I've got two appliances, and that's all I've got in this kitchen, or two pieces of kitchen equipment, then I'm going to have to take them at 100%. I don't get any demand. I take them at 100%. That's what the table says in 220.56. It is what it is. Okay? You take the full value. Okay? Now, so in moving beyond that, we're going to say, okay, well, what if I have more than two? Well, if that's the case, I've got some demand factors I get to do. Like it says here, you see that if I've got 3 units, number of units of equipment in this kitchen, then I've got, 90% demand I can apply. And if it's 4, I've got an 80. If it's 5, I got a 70. And if it's 6 or more, I can demand factor it down to 65%. So, again, if I've only got 2 things in here, maybe I only have commercial electric cooking equipment, 1 unit, and I have a dishwasher booster heater, and that's all I've got, well, that's only 2. I got to take them at their full value. Now, I start getting more than 2, and 3, 4, 5, and 6 and more, then I get to apply some additional demand factors to this loads that I'm talking about, okay? So, again, really got to know what equipment you're dealing with. And one thing to remember that table 220.56 does not apply to space heating, ventilating, and air conditioning equipment. It does not. We're talking about kitchen equipment. Again, a commercial cooking equipment, dishwasher boosters, water heaters, and other kitchen equipment that's designated for kitchen. It could be a big mixer in a kitchen. You have one of those big freestanding big industrial type commercial mixing things. And again, that's a piece of kitchen equipment, and that's how we would apply something like this to that. Okay? All right. The one thing it also reminds us that you should be aware of in 220.56, which most people won't pay attention to, is that in a kitchen you might have two larger pieces of equipment. And when you're doing a feeder or service calculation, you're applying all these things that we're doing for the general lighting and everything, the load that you come out after you apply all these demands, at the end of the day, the value for this load calculation for the service or feeder, it can't be less than the two largest pieces of kitchen equipment. Okay, and I think that's probably going to be rare happening, but you just have to remember that it can't be less. Whatever our calculation comes up by the process of everything we're doing here, if I were to add two of the largest pieces of equipment in that kitchen together, that service or feeder calculated load that we're sitting here doing, and we spent the last 45 minutes doing, can't result in a value that is less than what would be equivalent to the two largest pieces of equipment in a kitchen. Okay? That's all it's saying here. Okay? Probably never going to come into play, but you need to understand that that is there for a reason. So a feeder or service calculator can never be smaller than the combined rating of the two largest kitchen equipments in a load. And that's in 220.56. That's that last little paragraph that reminds me of that. Okay? Don't let that bog your mind, because that's probably rarely ever going to be a situation, but you just need to be aware of it. All right, so here was step 11. So if I got three or more pieces of equipment, and I'm going to use table 220.56, then I apply the demand factor. Okay, remember that doesn't apply to household cooking equipment used in institutional programs like maybe you're doing a school, but you have a home ec and they're using household ranges in there. You use 220.55 for that. You don't utilize 220.56 for that. Okay, just a reminder for that. Okay, all right, so that's what you're going to do in step 11. And it's pretty simple and straightforward. And you're adding that value down. You're just writing that value down. The next one is the step 12, and that's called non-coincidental loads. So here is where we compare the heat versus the AC. And we know that we take the fixed electric space heating elements, which is a fixed load, and it's fixed heating, then we take that at 100%. And that's what 220.51 tells us. You take that heating at 100%. Now the AC portion, you take at 100% based on its nameplate and everything that's associated with that AC cooling system. And you're going to compare the two. Now the one thing to remember is that if for some chance that you don't have the AC and the heat with the ability for them to come on simultaneously, it means whether the heat's on and the AC's not, or whether the AC's on and the heat's not, you get to take you have to take the larger of the two in the equation, and you can discount the lesser of the two. Okay, so I only have to take one, and that's what's called non-coincident loads. Now, if both of these loads are designed to possibly be on at the same time, then guess what? Maybe you have a building that a portion of the building is supplied by fixed electric space heating component, and another portion is air conditioning, and they might be able to run the air conditioning while the same the fixed electric heat is going. Then the problem with that is you'd have to count them both, because they're not inconsequential or non-consequential loads. They are both potentially running at the same time. So you need to keep that in mind, and you would have to equate them both. But if you have the ability where you have the fixed electric space heating loads and the AC loads and all of associated componentry aren't designed to run at the same time, then that is considered a non-coincident load, and I get to discount the lower of the two values. Okay. Most of the time, I'm going to tell you that fixed electric space heating, because it's just a pure load, that's going to be the one that wins. But again, not always the case. Okay, but I'm just saying, predominantly, that's the one that's going to pretty much rule the day. But just be aware, it's the larger of the AC versus heat, as long as they're non-coincidental loads. Okay? All right. And next, and that's step 12, and you write that step down. The next step that we're dealing with is motor loads. Now, I am not going to go into every aspect of motor loads, and you're sizing it based on 430.22, 430.24, and all of that things, or an AC compressor, which is also considered a refrigerant, AC motor-driven component under Article 440. I am not going to get into that in this because I have a video on that teaches you about motors and calculating all that, what the FLC is, and all those in order to calculate what our motor loads are. But whatever they would be, this is where it would go, okay, into this componentry right here, okay? So that's the kind of thing that you would work into this equation right here. All right, so once you know your motors, go watch that video on motors. You're going to plug it in right here as step 13. You go over to our YouTube channel. It's youtube.com/master the NEC, and you search for the video that's on motors. And it'll teach you everything you need to know about short circuit ground fault protection, feeder sizing, single conductor sizing to the motors, overload sizing, how to use the FLC tables in the back of 430. All of those type of things are covered. And there you'll get the understanding of what your load is and how you're going to add that here for all of the motors that are in your equation. Now, the only one thing that I'm going to add is when you're doing that whatever motors you have, the largest motor of all the ones you're calculating out, the largest motor, you want to take that one at 125%, okay? Or take its value and add 25% to that, okay? So find the largest motor and simply add 25% to that. And that's going to be the total of all your motor loads, okay, plus the additional 25% for that largest motor, okay? So again, in a simple way of saying that is add all your motor loads up, and find out which one's the largest, and then take that one and multiply that by 25% and add that value onto your motor load you just all added up, okay? Or, I guess you could take all of your motors, take the largest one, sit it to the side, add all of the other motors up and take that value, and then go add that motor up that you set to the side, which was the largest, and take that at 125%, and then add that value back to all the other motors, and that's the value you're going to put here in step 13. Okay? All right. Makes sense? Okay. Now, moving on to the last step of all of these different loads is what I call the catch-all step, which is the all other loads. So any of them that we haven't added at this point. And so at this point, people say, well, what about this? Oh, you forgot about that. Or what about this if it's on a drawing? This is where you catch it. If it's a piece of equipment, or a specific receptacle. Let's say I have a receptacle that's being utilized as a dedicated circuit to a piece of equipment that is cord and plug connected, and let's just say that piece of equipment is a continuous load. I'm just throwing it out there. Then this is where I would put this one in and calculate that out and determine that would be my 125% for this application here of all other loads. So any continuous loads that operate 3 hours or more, I'm going to take this at 125%, whatever that load may be. Okay, if it's 15 amps and that 15 amps load is done at 100 as a continuous load, then it's 15 times 125%. The load doesn't change; it's still 15 amps. But for use in the calculation, we have to take a load at 125%, even though that additional 25% is kind of invisible. It's just a fudge factor built in because the code says we have to adjust for that as a continuous load. Then that's what we're doing. Now, if the load is just a non-continuous load and we've got something that's not encompassed in this list here of everything we just went through, and it's still on the drawings, and we look at it and go, God, what category does that apply to? I didn't really touch that in anything that we did. Look at its appliance, look at its value, calculate out a VA, and if it's non-continuous, you just take it at whatever its VA is, and you add it right here. And you add all of them up right here in step 14. Okay? So at this point, we have steps 3 all the way up to step 14. Remember, 1 and 2 was just a combination of adding up receptacles before we applied a demand factor, right? So we're really trying to add up the totals between step 3 all the way up to step 14. Now, we add all those values up, okay? And now what we've got is what's called a total volt amp demand load. Now, once we have that demand load, now is when we can start sizing the minimum size service or feeder. And this is where we can get started. So now, you take whatever that value is, and that is going to be, again, your total VA demand load value. And I'm going to divide that by whatever the source voltage is. And if it's a single phase, then I would take whatever that VA value is and I would divide it by 240 volts. If it's three phase, then I have to remember that I use the square root of 3, 1.732, to come up with an actual value that we plug into this. And so, for example, if it's 208 volt three-phase system, then it would be 208 times 1.732, which is going to give us 360. So it would be whatever the VA is divided by 360. If it's a 480 volt three-phase, then that's just as simple. The 480 times 1.732. And then you're going to get with a 831, and that's the value you do here. So then it's this divided by that, and that's going to give you the minimum amperes. Okay, and that's the minimum amperes. Now, that's our calculated amps. We know it now. So now we have to size the service. Okay, now we know that we got to have a conductor that's going to at least handle this calculation for this load. We already calculated the load. We know that. We know that we need to do this. And we know that 230.42 tells us that, A. And then we know that 215.2 tells us that we have to handle that load. And we've done the calculation. We kind of know what the load is. But since, let's say, just for random numbers, let's say we did all this and we ended up with 216 amperes. That's what it was. Let's just throw a number out there. Now, I'm going to go to 240.6a and decide what is the rating of this service. If we're doing a service here, that's going to be 200, that can handle 216 amperes. So I go to 240.6a. I'm going to go with you, and I'm going to do that together. And I go to 240.6a, and you'll see this is a table there. And actually, the table's new in the 2017 code. Before, it was just kind of a rambling on in a paragraph. Now you got a nice little nifty table. And we're looking at 216. So when I look at the list here, I see a 200. And then I see a 225. I don't see anything in between that. So my selection is going to be 225. So that is going to be my minimum size service or feeder rating. So I write that down. That is going to be 225. You got me? All right. So that's that. That's my breaker. All right. Now, in that application, I want to find out what size conductors I need. And we know what the load is. Okay. The load was 216 amperes. I mean, that is the load. Okay, and one thing that we remember is this value that we're dealing with, 225 device, is not exceeding 800. Okay, not exceeding 800. So in that application, we're okay as far as with that. All right, so we're not losing sight of that. Okay, so in that calculation, we know that we only had a device rated at 225. Our load calculation was 216. Okay, so we got to do conductors. So we need to find a conductor that's ampacity rating can handle the load that we're dealing with. Now, we're not over 800 amps, so we're under 800, so 240.4b, and we're not talking about that equation yet. I'll talk about that in a second. So we need to have a conductor. So in our case, we're going to go to 310.15b16, okay, and determine what conductors can handle the 216 amperes. So when we look at 310.15b16, and we're going to assume copper, because we always want to assume copper if we're doing an exam, we want to assume copper. And we're going to go to the 75-degree column, because generally that's going to be your terminal limitations that we're going to have to devices and things like that. So again, I'm going to give you a given, 75C. And we're going to go down here, and I have to have a conductor. So it looks like I've got a 4-aught copper, which is good for 230, and my calculated load was 216. And so I'm okay there. And I got a 230 amp rated conductor. And can I use a 230 amp rated conductor on a 225 amp rated breaker? Absolutely. It's fine there. So I'm good. So here, my size would be a 4-aught, which is good for 230 amperes. Okay? So that's my scenario when I'm dealing with that, and that's how I'm going to size the conductor. Now, let's talk about conductor's ampacity rating, where it might be on an overcurrent device that exceeds 800 amperes. If that's the case, then my conductor's ampacity, does, in that scenario, if I had an overcurrent device that was over 800 amps, then my conductors have to have the capacity and the ampere rating equal to or greater than whatever the value is that we're doing as far as our overcurrent device. But since ours is under 800 amperes, I don't have to do that, and that's what allows me to utilize the next size up rule and still consider protecting those conductors, all in accordance with 240.4b. Okay, so that's how we do it. Now, I will remind you that if you have any adjustment or corrections that come into play, let's say you have 3 or more current carrying conductors, then I'm going to have to bring in the equation of 31015B3A and work that in as well. Typically for the service, we're probably not going to have an application where we have more than 3 current carrying conductors, but for a feeder, we might absolutely have that scenario, and we have to take that into consideration. The other thing that we have to take into consideration is we could have a situation of ambient temperatures, 31015B2A, that might have to come into play, and you just need to be aware of that when you're doing that. So that's how we size our conductors at that point. We also want to remember some golden rules here. If we're going to run parallel conductors, and there's a chance we're not with this size service because it was way too small. But if we had to run into a set where it was over 800 amperes and those conductors needed to have a certain amount of current carrying capacity that we decided to run parallel sets, then they can't be smaller than 1 aught, okay? And the parallel sets have to be joined at both ends in accordance with 310.10H1 and all those rules with paralleling we have to take into consideration, okay? And the other thing to remember is if we were dealing with an over 800 amperes and we were paralleling, the cumulative total of circular mills and the ampacity values of that total sets have to be equivalent or greater than whatever the rating is the overcurrent device is if we're over 800 amps. Again, under 800, we got next size rules that we can utilize. Over 800, then we really don't have that luxury, and we have to make sure that our conductors are sized to handle fully whatever the rating is of the overcurrent device. That's the general rules that we want to follow and leave it simply at that. So, one warning I just give people. For overcurrent rated devices that are rated 800 amps, okay, over 800 amps, the ampacity of a conductor's protection shall equal or exceed the rating of the overcurrent devices that are listed in 240.6, and it's referenced in 240.4c. Do not exceed the temperature limitations outlined in 110.14c. Okay, so the use of 90-degree ratings for adjustment and corrections and derating for the number of current carrying conductors can be utilized, but you're still going to be limited to the terminals, okay? You're still going to be limited, and that's going to be all governed under 110.14c, so just don't lose sight of that as you're going through all this. All I wanted to do is show you the different steps and work you through the different steps of how to do this. Hopefully you got something out of that. Now, when you're doing the neutral load, because we just did everything else, when you're doing the neutral load, you have to remember a couple things when you're calculating this neutral. So to size this neutral, let's kind of go back and look at all of the calculations that we just did. All right, any of the lighting and receptacle loads that we just did that were 120 volt loads are neutral loads. So you go back and you make a little circle, let's say a dot, next to all of those loads that we calculated that were utilizing 120 volts. Okay? All your lighting loads, all your receptacle loads, and all those general use ones are going to be 120. Okay, those values, you need that value. That's the same value you already calculated it. It's already been done. You just put a dot beside it because that's what you're going to need. The next thing you want to look at is any appliances, equipment, motors, or etc. that actually utilize a grounded neutral conductor, okay, are to be included in this neutral calculation. So you have to look down in all of those motors, all of those appliances. If they utilize a grounded conductor, then that has to be calculated with your neutral conductor, okay? It has to be sized, okay? Now, taking neutrals a little further so that you can understand the neutral, because we've already done the loads. We're good with the loads. Now we have to look at some of the rules that are in 220.61, and whether you're doing a feeder or service, the neutral load is what is it? It's the maximum unbalanced of the load determined by Article 220, and that's just what we've done. We systematically calculated things out, okay, in our method of how we apply it. We just sit there and we just went through each step of this thing. Now, you are allowed to apply a demand factor, believe it or not, to the neutral calculation, okay? So under 220.61, you'll see that a 70% demand factor is permitted for that portion of the unbalanced load that's above 200 amperes. So let's say I've got 300 amperes of neutral load, and that's what I've calculated out based on all of my connections that utilize a neutral conductor. Or in our case, when we say neutral is used as a grounded conductor. We're going to kind of keep them synonymous for the purpose of this calculation, so we know that they are kind of mutually the same. You always have when you have a grounded system, you always have a grounded system, but you don't always have a neutral. But in our case, I'll explain something about that in a second. But we're going to say we're talking neutrals right now, and it means the same as grounded, so that we're keeping it simple. All right, so if we had 300 amps of neutral load based on our calculations here in 220.61, we get to take the first 200, so we just take that point blank. We write 200. That's the first neutral load. Now, the portion that's over that, we're able to take 70% demand of that. And so our portion over 200 in our case was 100, okay, because we said we had 300 amps. So that 100 amps, I get to take that at 70% demand. So in our case, that would be 70 amps, because it's 70% of 100 is 70. So I have 270 amps of neutral conductor load, and I would size my conductor according to that. Okay. Another thing to remember is, in no case can the grounded conductor, in our case neutral, cannot be smaller than what's specified in 250.24c1, which ultimately is going to send me to 250.102c1. Okay, so it can't be smaller than that, but it could be larger than those tables based on having to do a calculation. So you're going to take the larger of the two, but it can't be any smaller than the values that we calculate out in 250.102c1 based on the size of the service conductors, for example. That's what we're going to use to dictate it. So we have to remember that we do have the ability to apply demand factor here. Okay, so we can do that. All right. Now, that neutral is to be sized by finding the maximum unbalanced load, and that's what we found. In this case, it was 300 amps. It was 100 of it over 200. We applied 70% to the amount that was over 200, and that was 207 amps, and that was our neutral load. Now, let's use a little bit of caution here when we're understanding the reduction of the neutral's capacity and what we can and what we can't do. Okay. Now, this reduction, this 70% reduction that can be applied, okay, only applies if the system is a single-phase AC or a 4-wire 3-phase system or a 4-wire 2-phase system or a 5-wire 2-phase system. Then I can apply this application, all right? This allows me to reduce the size, or a permitted reduction. So that's what we're doing. We're permitted reduction here on the neutral, all right? Why is that important? Now, the reason is because the reduction of a neutral's capacity is not permitted for that portion of a load consisting of nonlinear loads that are supplied by a 4-wire Y-connected 3-phase system, nor the grounded conductor of a 3-wire circuit consisting of 2-phase wires and a neutral that are derived from a 4-wire 3-phase Y-connected system. Okay? So if that's the application, then those are prohibited in having a reduction. And that is all listed here in 220.61. You have the permitted reduction in B, and then of course you have the prohibited reduction in that neutral side in C. Okay? And basically it says in C, the prohibited reduction says there shall be no reduction of the neutral or grounded conductor capacity applied to the amount in 220.61C1 or a portion of the amount in C2 from that determined by the basic calculations. Okay? So, there is a permitted reduction and then there is a prohibited reduction. Okay? And you need to look at which one it is when you're dealing with that. Now, some people will say, look, I am going to just simply size my neutral conductor the same size as my phase conductors, and, wham, bam, thank you, ma'am, and I'm done. Okay? They might apply that, and you just simply walk away. All right? But I think it's important that you understand how to apply all those things and how to utilize it when you're doing this type of calculation for load. So, anyway, it was a little over an hour. I probably could have slowed it down a little bit, but hopefully you got it. I could give you a summary, but again, what's the point? You've got a number of steps that you follow, and so hopefully you follow those out. And you have any questions, you can always email us at info@masterthenec.com. Look, I have a healthy understanding that some people will agree and disagree or say that I wasn't detailed or I was over detailed or whatever. At that point, those that are critics, I'm eagerly awaiting your podcast and your ability to teach other people, because I doubt you probably can. Because you're probably one of those that just sit back on a couch and want to complain about everybody else, and you probably don't contribute any to helping other people, which is a sad thing. For all of you that do listen to these podcasts and watch those videos, I know that you want to learn, you're dedicated to learning, and that's what I'm here for. We don't worry about those other naysayers and negative people. You know what? They can live in their own misery, because some people simply love misery. You know what I'm saying? So anyway, hopefully you got something out of it. Again, you can email us at info@masterthenec.com. If you have any questions, you can go to our website at masterthenec.com or electricalcodeacademy.com and click on the Contact Us button and fill in your question there. And you can go to our Facebook page and type your question in there. I really don't care. I don't mind what questions you ask. I do not mind if you question me. I do not. I love it. I love the opportunity to explain it in more detail. I get text messages and calls and people wanting to explain stuff all the time. And I'm trying to remember, guys, this is a lot to learn in a little over an hour, and there's no way that you can take it all in. And I'm talking so quickly that I might have kind of skated over something and got you confused, and I totally get it. Give me the opportunity to clarify it, and I will explain it to you in detail. Whatever helps you out, I'm here to help you. So until next time, folks, stay safe, and God bless.
Every day, the future's getting closer. Every day, the future's looking bright. Every day is another beginning.